Hello everybody, my name is Guzauckas, and today we're going to learn how to graph points on the 3D coordinate plane. Well, it's not a plane anymore. We are used to our traditional two-dimensional plane where it is x and y. We have y over here and x over here, but the third dimension adds the variable z, which adds depth to the xy plane, which is why xy is kind of flat, like my hand, and then z pokes out and gives it height. Now, plotting in 3 dimensions isn't too difficult. It obviously has a little bit more of a challenge than 2 dimensions, but it's not too bad. So let's plot the point 1, 2, 4. Now, if you're not familiar, we have y, and we have z. Usually it's just x and y, but when you add the third dimension, you just add the next dimension. That can work up to any number of dimensions as you go on. But for now we have our x is 1, our y is 2, and our z is 4. So this is actually, graphing 3D coordinates is a 3-step process. The first step is to graph your x. Now this sounds kind of not very right, but it'll make sense as we go on. So we start with our x. Now our x is equal to 1, and this is our x down here. So this is 5, which means we're on a one step. So x equals 1 would be right there. Now the second step is x, comma, y. Now what this means is that just using the x and the y, we're going to graph them as if it was a coordinate by itself. So 1, comma, 2. Now, we already know how to do 1, 2, since that's just 2 dimensions, but this looks a little different, right? All of a sudden the x is diagonal. So let's look at this. 2 on the y is right there, right? And then our x is 1 is right here. So now we could take it out, but as we notice, instead of it being a right angle like the y and the z are, like our traditional x and y are, it's diagonal. So what we do is we copy that diagonal over here, and we call this the parallelogram rule, where you draw a parallelogram to reach the correct position of the point, and the angle of the parallelogram is the angle the x-axis is off of the rest. So we see we have a diagonal here, and then it meets here, and there is our xy. So if we label these quick, this is the point 1. That's it. And then this is the point 1, comma, 2. Now, we're almost there. All we have left now is to add on the z, and that's the third step. Graph x, y, and z. So now we know where 1, 2 is, but now what we see is that when z is 0, we're not actually on the line, or what we would think would be the line. So what we do here is we look at 4. 4 would technically, if we thought about it, should be there, where it's straight up from the red. But in reality, we have to mark it down this much in order to make it legible or correct from the 1, 2. So you can see here, we can draw a dotted line down to where our point 1, 2 is and this is, although it looks like it's only 3 units up, because this right here is 3, it's actually 4 units up because of this little distance down here. So we have the point 1, 2, 4. So let's review this process quick. We started off with our x. Right here we had the point 1 on the x-axis. Then we went to our second step, which is x, comma, y. We added in the y-coordinate, we moved over, and we used the parallelogram rule in order to get the right point. And we had the point 1, comma, 2, which was x, comma, y. And then finally, we added in our z by adding the height, which looks incorrect, but in reality is very close to our 4 right there. Now, we're going to add in negative values to these coordinates. So if we look at it, our x, since it's diagonal, this is looking at it, this is flat, and then the x goes behind it. The dotted lines represents diagonals behind the regular 3D coordinate plane. So this is our negative y, this is our negative z, and this is our negative x. So we're going to graph a point that has some positives and some negatives to kind of give you an idea of how they interact. So let's take the point -1, -2, 4. So this is very similar, well, it looks very similar to our last point where it was 1, 2, 4, but now we added in negatives for 2 of the 3 values. So now we're going to bring us back, this is going to bring us back to our original process where we go x, then x comma y, and then x, y, z. So let's start out with our x. So if we look at it, this is based on the steps, this is about 1. So our x is equal to -1, since this is in the negative direction, will be right there. So that's fairly simple. That's the point -1. Now, if we take our xy, we notice something interesting. So we take 2 steps back. Now this is -2, but again, we bring ourselves to the same predicament we had here with the parallelogram rule. So we look at the diagonal that the x-axis makes, and we kind of copy that up until we get to the right height. So the right height is about right there, so that is where our point is. So that is, in reality, lined up with -2 on the y-axis, although it doesn't look lined up, so that's the point, -1, -2. Now, you know, I'm going to have to move that over. -1, -2. Now, we bring ourselves to our final x, y, z. So now we talked about before how the actual value of the z-axis is relative to how far away you are from the origin. So we have 5 up here, but we're almost at, well, this is the 1 mark right here, we're almost at 1 already on the z-axis, so we have to add 4. So we're going to take this space and then bring it off up from 4, and that's about the height. So let's bring a straight line up. That is where our point -1, -2, and 4 would be placed, because if you think about it, our -1 goes in the opposite direction of the x-axis, right? This is the x-axis, beyond to the -1. Then, using the parallelogram rule, we lined it up with -2 on the y, and then finally, using the relative space we have here between the origin and where we are on the z-axis, we use that relativeness to find where 4 would be lined up on the z-axis. So this right here is the point -1, -2, 4. Thank you for watching. Be on the lookout for more videos. We're going to be doing more with 3 dimensions and what we can do with them that's different from 2 dimensions. Thank you.